Welcome to a webcast made by the Learning Enhancement team based in the Dean of Students office at the University of East Anglia. This webcast is part of the Steps into Calculus series and concerns differentiating y equals ax to the power n. This guide describes how to differentiate functions of the form y equals ax to the power n. It identifies the various forms that these functions take and introduces the power rule of differentiation to find their derivatives. Introduction. Many functions take the form y equals ax to the power n, where n is the power of the variable x and a is called the coefficient of x. Functions of this type are usually the first that you learn to differentiate. They cover a wide range of mathematics that you may have already come across. Specifically, they describe straight lines, polynomials such as quadratic and cubic functions, reciprocals and roots. Value of n 0, type of function constant, example y equals 5, value of n 1, type of function straight line, example y equals 6x, value of n positive whole number greater than 1, type of function quadratic, cubic and so on, example y equals 4 times x to the 5, value of n negative whole number, type of function reciprocal, example y equals 1 divided by x cubed, value of n fraction, type of function containing a root, example y equals the square root of x. These functions can be differentiated by using the power rule of differentiation, which is usually the first major rule you encounter when learning calculus. The study guide, What is Differentiation, can help you understand the terminology of calculus. The power rule is a two-part formula for finding the derivative of a function of the form y equals ax to the n. So specifically, if y equals ax to the power n, then the derivative dy by dx equals a multiplied by n multiplied by x to the power n minus 1, where n is the power of x and a is the coefficient. To use the power rule successfully, you will need to become comfortable with how these two parts interact. To begin with, you must be able to identify those functions which can be differentiated using the rule. The rule depends on you being able to identify the values of a and n from the first part of the rule and substituting them correctly into the second part. It may be necessary to manipulate a function to see that it fits the pattern of y equals ax to the n. As differentiation naturally follows on from algebra in mathematical studies, you need to be comfortable with the many skills and techniques involved in algebra to help you with the processes and concepts of differentiation. A good understanding of the laws of indices and the rules of arithmetic involving fractions are essential. See study guides, multiplying and dividing fractions, cancelling down fractions, multiplying and dividing algebraic fractions, and laws of indices. You should also be familiar with the concept of a function. See study guides, functions, and using functions. Using the power rule. The rest of this guide contains examples of the variety of functions which can be differentiated using the power rule. The examples will cover a variety of different cases for a and n and are chosen to highlight common difficulties. 1. Horizontal lines. See study guide, the straight line. Horizontal lines are represented by the equation y equals a. This function does not look like y equals ax to the n at the moment, and so you may think that you cannot use the power rule to differentiate it. However, the laws of indices tell you that x to the power 0 equals 1, and so as y equals a multiplied by 1, replacing the 1 with x to the power 0 gives y equals a multiplied by x to the power 0, where the dot implies multiplication. By thinking about the graph that the equation represents, you may gain some insight into its derivative. Remember that the gradient of a graph is given by its derivative and by the change in y divided by the change in x. For a horizontal line, the change in y is 0, and so the gradient of a horizontal line is also 0. This is an important result that is reflected in the fact that the derivative of a constant is 0. Example: differentiate y equals 2. As y equals 2 is a horizontal line, as shown by this graph, you already know that its gradient is 0. If you can correctly identify a and n in the first part of the power rule, you can use the second part to differentiate the function. It may help to write the first part of the power rule underneath the function to help you see a and n. Using the laws of indices, you can rewrite y equals 2 as y equals 2 multiplied by x to the 0. Now, write the first part of the power rule underneath. From the pattern of the first part, you can identify a equals 2 and n equals 0. Remember that n is the power of x and a is the coefficient of x. For horizontal graphs, a is always the constant in the function. As you know a and n, you can use the second part of the power rule to find the derivative. dy by dx equals 2, which is a, multiplied by 0, which is n, multiplied by x to the power 0 minus 1. This equals 0, and so y equals 2 has a gradient of 0. 2. Straight lines of the form y equals ax to the n. See study guide, the straight line. Functions of the form y equals ax to the n with n equals 1 can be written as y equals ax. These functions represent straight lines with a gradient a which pass through the origin. As the gradient of any line is given by its derivative, the derivative of y equals ax must equal a. So, intuitively, the value of a in a function of this type should give the same result as the power rule of differentiation. Example: what is the gradient of y equals minus 7x? As y equals minus 7x is a straight line through the origin, see graph below, its gradient is given by the coefficient of x, which is minus 7. You can use the laws of indices to rewrite y equals minus 7x as y equals minus 7 multiplied by x to the power 1, and so use the power rule. Y equals minus 7x is the same as y equals minus 7x to the power 1. This gives a equals minus 7 and n equals 1. As your function fits the pattern for the first part of the power rule, you can use the second part to find the derivative. dy by dx equals a multiplied by n multiplied by x to the power n minus 1, which in this case equals minus 7, which is a, multiplied by 1, which is n, multiplied by x to the power 1 minus 1, which equals minus 7 multiplied by x to the 0, which equals minus 7. So, y equals minus 7x has a derivative of minus 7, which is the same as the expected gradient. The covering up method. A useful method to find a in the power rule is to cover up x and its power. What remains is the value of a. For example, in y equals minus 7x, if you cover up the x, you have minus 7 remaining, which is the correct value of a. Example: differentiate y equals x divided by 3. It is not as easy to identify a in this example. A common error is to say that a is 3. However, you should be careful when your function is a fraction. By using your knowledge of how fractions multiply together, as well as the laws of indices, you can rewrite the function as y equals x divided by 3 equals 1/3 multiplied by x divided by 1 which equals 1/3 multiplied by x to the power 1. So this gives a equals 1/3 and n equals 1, as shown in the graph to the right. You can use these values in the second part of the power rule. dy by dx equals a multiplied by n multiplied by x to the power n minus 1, which equals 1/3, which is a, multiplied by 1, which is n, multiplied by x to the power 1 subtract 1, which equals 1/3 multiplied by x to the power 0, which equals 1/3. The function is a straight line with a gradient of 1/3 which passes through the origin, as shown in the graph above. 3. Positive whole powers of x. A very common type of function to be required to differentiate has n as a positive whole number. Example: differentiate y equals 6x cubed and then find its gradient at x equals 3. The graph of y equals 6x cubed is given here. Here the function obviously fits the first part of the power rule. Y equals 6x cubed, writing the first part of the power rule underneath, with a equals 6 and n equals 3. You can cover up x to the power 3 to see that a equals 6, like this. Using these values in the second part of the power rule gives dy by dx equals a multiplied by n multiplied by x to the power n minus 1, which equals 6, which is a, multiplied by 3, which is n, multiplied by x to the power 3 minus 1, which equals 18x squared. The derivative 18x squared describes the gradient of y equals 6x cubed at every point on its graph. You should realise that the gradient of y equals 6x cubed changes as x changes, as its derivative is a function of x. To find the gradient when x is equal to 3, or indeed at any point, you substitute the value into the derivative function. dy by dx equals 18x squared, which equals 18 multiplied by 3 squared, substituting in the value x is equal to 3, which equals 162. On the graph below, the dotted line illustrates the tangent on the curve when x is equal to 3. Here is x equal to 3, and here is its tangent. Calculus confirms that the gradient of this line is 162. Example: with the coefficient hidden. Differentiate y equals x to the power 4. In order to use the power rule, you need to rewrite the function to fit the pattern, because the coefficient a seems to be missing from y equals x to the power 4. Remember, you can always multiply something by 1 and keep it the same, so the function can be rewritten as y equals 1 multiplied by x to the power 4. Often, when the coefficient is absent, it is assumed that its value is 0, which is not the case. If it were 0, then the whole function would be 0, as anything multiplied by 0 is 0. However, using y equals 1 multiplied by x to the power 4, you can use the first part of the power rule. Y equals 1 multiplied by x to the power 4, writing the first part of the power rule underneath, giving a equals 1 and n equals 4. You can use these values in the second part of the power rule to find the derivative. dy by dx equals a multiplied by n multiplied by x to the power n minus 1, which equals 1, which is a, multiplied by 4, which is n, multiplied by x to the power 4 minus 1, which equals 4x cubed. So, the derivative of y to the power 4 is 4x cubed. Example: with fractional coefficient. Differentiate y equals 5x cubed divided by 6. Again, this example does not perfectly fit the pattern for the power rule, and you should take care when deciding the value of a. You can cover up x cubed to find that the value of a is 5/6, or you can rewrite the function as y equals 5x cubed over 6 equals 5 over 6 multiplied by x cubed over 1, which equals 5 over 6 multiplied by x cubed, showing that a equals 5 over 6 and n equals 3. You can use these values in the second part of the power rule to find the derivative. dy by dx equals a multiplied by n multiplied by x to the power n minus 1, which equals 5 over 6, which is a, multiplied by 3, which is n, multiplied by x to the power 3 minus 1, which equals 5 over 2 multiplied by x squared, which equals 5x squared over 2, where the derivative function has been cancelled down to give the simplest form. 4. Negative whole powers of x. Reciprocals. When x appears beneath the dividing line, it is extremely common to assign an incorrect value for n. However, by recalling the law of indices, 1 over x to the m equals x to the minus m for non-zero m, helps you rewrite these functions in a form which matches the first part of the power rule. Example: differentiate y equals 3 divided by x to the power 5. You may think that n is 5 in this question, but by using the laws of indices mentioned above, you can see that y equals 3 divided by x to the power 5 equals 3 over 1 multiplied by 1 over x to the power 5, which equals 3 multiplied by x to the power minus 5, which fits the pattern of the first part of the power rule with a equals 3 and n equals minus 5. You can use these values in the second part of the power rule to find the derivative. dy by dx equals a multiplied by n multiplied by x to the power n minus 1, which equals 3 multiplied by minus 5, use brackets to help you here, multiplied by x to the power minus 5 minus 1, which equals minus 15 multiplied by x to the power minus 6, which equals minus 15 divided by x to the power 6, where the derivative function is written in the form of the question with x beneath the dividing line. 5. Powers of x which are unit fractions. Roots. You can use the law of indices. The mth root of x equals x to the power 1 over m to help you differentiate functions which contain a root. Example: differentiate y equals 8 multiplied by the square root of x. By using the law of indices mentioned above, you can see that y equals 8 multiplied by the square root of x equals 8 multiplied by x to the power half, which fits the pattern of the first part of the power rule with a equals 8 and n equals a half. You can use these values in the second part of the power rule to find the derivative. dy by dx equals a multiplied by n multiplied by x to the power n minus 1, which equals 8, which is a, multiplied by a half, which is n, multiplied by x to the power a half minus 1, which equals 4 multiplied by x to the power minus a half, which equals 4 divided by x to the power a half, which equals 4 divided by the square root of x, where the derivative function is written in the form of the question as a root. Further guidance and information. If you have any further questions about calculus or would like to discuss any other aspects of mathematics, you can talk to your lecturer or personal advisor or make an appointment to see a learning enhancement tutor in the Dean of Students office. Telephone 01603 592761. Email dos.help@uea.ac.uk or visit our website at www.uea.ac.uk/dos/let. There are further resources on many other aspects of calculus, mathematics, statistics and science available from the Dean of Students Office and on its website. These include questions to practice, model solutions and webcasts illustrating essential skills.